us this morning for the meshless CFD presentation using the moving particle simulation, discussing gear oil, lubrication, aeration, and splashing. Today we're going to talk about, for just a few minutes, the company of EngineSoft. EngineSoft itself was started as 1983 as a group of engineers. It's based in Padua, Italy. We provide customer solutions to leading companies throughout the world. We have over 200 experts in engineering and specialize in computer-aided engineering, FEA, CFD, and other types of CAE. Our offices are spread throughout the world. We have, of course, the offices here in the United States. We're based in the Dallas area. We also have offices in multiple locations in Europe, and our offices in Dallas are in the North Dallas and McKinney area. Throughout the years, we've had the pleasure of doing business with a lot of different companies, and those companies include different logos, as you see here, with a heavy focus in companies that really make complex products and those that need to have advanced CAE functionality, both from a FEA perspective, a multibody dynamics, and of course for this discussion, the moving particle simulation is used primarily in automotive companies, although there's also some in the applications for retail. What distinguishes us from other companies? Well, we have over 4,000 consulting projects. We do training. We have software implementations that we've done over 1,000 times. And for the consulting itself, 120 plus engineers and 4,000 projects throughout all of the different industries. Our software resale business includes Creo products, Recordine, Paricleworks, which is the one we're going to be discussing today, as well as the service offerings with some of the other partner softwares. We do training throughout the United States and even have an international CAE conference in October, which about 300 to 400 different engineers come to from around the world. We do partner with government institutions for research, and that research is associated with both the Italian ministry and the European Union, and also SBIR projects in the United States. Our skills are covering the main areas of analysis work. So, of course, the fluids, the mechanical tolerance, vibration, optimization, and multibody. And we use a variety of different technologies. So we'll skip through that. The approach that we use is working with our customers, and that enables us to have the reliability that we need for the customers in order to improve their design processes. With that, I will turn it over to James, who will start to talk about giving the actual presentation for MPS.
Thank you, Chris. My name is James Christ. I'm a senior application engineer with EngineSoft. And just a little bit of housekeeping before we get into the more technical portion. Towards the bottom of your screen, you should see an option to both chat and raise your hand. So if you have questions as we're going through, would be happy to answer those. Okay, so on the slide deck, we're going to cover some of the theory behind the Paricleworks method, and then a couple of the applications, as well as some of the things that you can do other than gearbox analysis. And then we'll jump into a live demo where you'll see the process of somebody actually setting up and starting to run a simulation. So Paricleworks is a specialized solver that focuses on free surface flows. So it's particularly useful for gearbox analysis, where you've got like a sparsely populated domain and a very dynamic free surface environment. The method was created in the mid-90s out of the University of Tokyo by the person who would later co-found Prometech Software, the manufacturers of Paricleworks. And if you're familiar with SPH, or smooth particle hydrodynamics, it shares a lot in common with that method. This is really a specialized form of SPH for incompressible flows, and it's able to do those subsets of problems much more efficiently. and it's a Lagrangian method. So compared to a conventional CFD method where you've got a fixed grid, you're attaching calculation nodes to the fluid volume, and then following those through the domain. Kind of the 2D understanding of the method is here. So on a conventional method, you would have a fixed grid, and then you would assign a mass fraction or volume fraction to some of those nodes, and then carry that mass fraction throughout the simulation and solve for that on every point in the domain. With the moving particle simulation method, instead you just define where your walls are and then where you are starting off with fluid, and those are the only calculation points. As we move through the simulation, the Lagrangian method, carries through those calculation points and dynamically draws connections between nodes throughout the simulation. So that's kind of why we call it a particle-based method. You're evaluating fluid properties at each particle rather than in a fixed way. And there's two large advantages that you get with a method like this. So first, from the computational side, you're not evaluating fluid properties where you are, resulting in essentially a null value. So we're not spending time calculating that there's no fluid right here, which we are on the conventional finite volume side. And the other thing is that you have to make a lot of assumptions in setting up your mesh beforehand. So we have to predict where the fluid is and where we want to resolve features. Whereas with the MPS method, we set our particle size analogous to a grid size based on the smallest feature that we want to resolve, and then we're able to carry that through the entire domain. So we're not picking and choosing where we're resolving small features. One thing that I like to mention is that the method applies to both Newtonian and non-Newtonian fluids. For a gearbox simulation, you're almost always Newtonian, but I do like to mention that. So a couple of practical examples. So this is something that a real company would have to analyze. So we've got a gearbox with some initial state of fluid, and then we want to see where that fluid is moving over time. And we're able to do very large timescale problems compared to a finite volume method. So here we're doing 2 seconds, I believe, over 2 seconds, and seeing how this fluid is moving about. And we're able to do this in a computationally efficient way in a reasonable period of time. Another application, so inside of a crankcase, at different RPM speeds, you might want to look at, are we getting proper lubrication coverage in every location? What's the difference if we have different fill levels to begin with, and what happens if we use different oil properties? So you're able to iterate over designs very quickly. This is probably one of my favorite examples. So direct comparison to a finite volume method, star CCM. And it really shows one of the big advantages as far as time goes, because you can see that setting up this problem without any moving parts on star CCM side took 2 weeks. So that can be prohibitive if you're trying to iterate on designs versus just a single day. And you'll see why when we do an entire problem setup in the live demo. So from a human time perspective, the difference is massive. And then also from a computational standpoint, with 4 times the resources solving a computationally simpler problem, it took the same amount of time, or star CCM took the same amount of time as Paricleworks to compute a solution. This is an example of a customer, Comer Industries, over in Italy, and they were really interested in moving to simulation, but they needed to hit very aggressive simulation time targets because they were able to do live benchmarking or prototyping in less than a week. So they needed to beat that to meet their actual design process. So their design process before they moved to Paricleworks was to just build a prototype, put a clear case on top, and then based on their own experience, they knew what kind of flow patterns they were looking for at the top. So that gave them something to compare to when they were doing simulation. But in their experience, that took much too long to do in a computer versus building a prototype. With Particleworks, we were not only able to hit that target, we were able to do it in a reasonable period of time. And then as they moved to a simulated environment, they're able to look not just at a top case and then take it apart and look at wear or something like that. They can actually look at fluid moving around internally that you pretty much are never going to be able to measure on a live prototype. So they were interested in the lubrication of this bearing, and they had these flow channels that are supposed to direct fluid over the bearing, and they were able to directly measure flow rates and then make designs more efficient, set proper oil levels, things like that. And to run this simulation using a mesh-based CFD would have taken about 2 weeks, a week or two, which is already longer than it was taking them to prototype. With the MPS method, they can do the whole problem setup in less than a day. And then to actually compute solutions, again with the mesh-based CFD, really time prohibitive. It's never going to be practical for their problems, whereas MPS could do that problem in enough simulated time in only a few days, and using a very reasonable amount of computing hardware. Oftentimes, we're seeing people use hundreds of cores on a large cluster for a mesh-based CFD, and those just become very complex systems from a computer hardware standpoint to maintain and to purchase versus just running it on a single workstation. And we're able to do even more of that by offloading to a GPU because the MPS method is so parallelized, whereas it's kind of hit or miss whether a mesh-based CFD is even going to be able to run on a GPU. So at the end of the day, they found they could run the simulations in less time than it took them to prototype versus the mesh-based CFD, which took over a month. And one last success story from a customer, Dana Corporation. They were really interested in several things, but in this case, they wanted to look at churning losses and lubrication properties. So they ran this simulation and then compared this axle to lab tests that they had done, and they found extremely good results. And they actually wrote a paper about that. So if you're interested, please reach out. We might even include it in the follow-up email that you'll be getting. So speaking of churning losses, that's another thing that we can provide using this method. So this is just a simple example, but it demonstrates the kind of problem that you would need to see. Well, what kind of losses am I getting in that gear? And we can split it out. This is a standard output, and we can split it out by viscosity and pressure gradient torques. Now, I'll go through a couple of the more specialized examples. So thermal analysis is something that's supported with the MPS method, and the typical workflow that, for example, Wärtsilä in this example is using is they'll run Particleworks to get a heat transfer coefficient, in this case on piston walls, and then they'll run a longer term FEA thermal analysis to get the actual temperature distribution. And this is on the Particleworks side, the actual particles and then the heat transfer coefficient mapped onto the internal walls of this tube. So then they can pull that information out and set it as a boundary condition using their FEA tool. And this is something that's actually become easier to do. In the past couple of weeks, an ANSYS Workbench plugin was just released. So instead of having to manually do some of this export and import, that's become easier. You can just kind of drag a button around. Another coupling that we have is with Recordine. So this is for multi-body simulation. In cases where you can't just use prescribed motion, in most cases we can just use prescribed motion to define how fast gears are moving. For a complex example like this where you've got a chain, that's not something that you're going to be able to just prescribe. So We can run these as a one or two-way coupled simulation. And this is an example down here of what happens when you have the fluid exerting the pressure or force on this chain. So on the left, we just have prescribed motion set by the multibody solver, and on the right we have a two-way coupling interaction. This is also valuable when you have systems where the motion of the fluid is a significant like mass portion of the whole system. So for a motorcycle, the oil volume can affect the vehicle dynamics. So, as you're going through a turn or as you're just kind of bouncing around, that oil can have a significant effect. We can also interact with velocity flow fields. So because we're using an incompressible method, we can't solve for air directly, but we can bring in flow fields for systems where the fluid volume isn't exerting a large force on the air field. So in this example, we've got let's see, here we go. So we've got rain splashing off of a windshield. The rain isn't having a significant effect on the actual wind. So we can just have the wind affect the water coming down. Okay, and with that, if we have any questions, we can do those now, or we can wait until after or during the live demo. But we'll go ahead and switch over to my colleague, Chris Garcia, and he's going to walk you through actually setting up a problem in Paricleworks.
Good morning, everybody.
Okay,
See if I can get my screen going here. Okay, can everybody see my screen?
I believe we can.
Okay, perfect. So just to kind of give you a brief introduction, my name is Chris Garcia. I'm a CFD engineer slash sales engineer here at EngineSoft USA. And this morning I'd like to go through a brief demo of just setting up a model and just kind of showing how easy it is to get this stuff going and kind of point out a few functionalities. I won't go too heavy into detail. I'll try to keep it as brief as I can. And we'll get this going. So Particleworks is one software that defines a project. You can read geometry, set up simulation, run simulation, and do some post-processing. So I'm going to go ahead and start. I'm going to start a new project. This is already my defined location. Just going to call this Gearbox demo. Finish. And perfect. So you should get this little icon here. I'm going to go ahead and double click on this scene, and this will give me an empty box. This is where you can import your geometry, all your material properties, and run your simulation here. So first step is to open up what we call the startup wizard. This startup wizard is a guided procedure for importing objects, setting up boundary conditions, material properties, setting up numerical settings, and then starting the simulation. So I'm going to go ahead and do that. I'm going to open up this model. And the nice thing about it is you can import all these objects all at once. Time. Perfect. So now you can see this is our model that we want to run a quick simulation on. And let me do a quick adjustment real quick. All right, perfect. And let's go ahead and make this visible. Nice part about Particleworks is that you can essentially hide some features and see what's actually happening. You can see the gears and the shaft inside this scene, and it'll be nice to visualize the actual simulation happening. So from here, I'm going to go ahead and set up a domain for this system. This domain essentially contains all the elements within our geometry. You can see here that this yellow box is your domain definition. Okay. Now I want to get in here and let's do a little bit of motion in these gears. So I'm going to click on this shaft in. It'll highlight in a yellow. And just so I can give a little differentiation, I'm going to change the color on this. I'm just going to do just some kind of red. Perfect. All right. So now I want to set up the motion in the z-axis for this shaft. Excuse me. And I'm going to do that by going into this keyframes, which can be found in this outline tab. I'm going to change this and key from location X to rotation. And I'm going to change this to rotational speed. I'm going to change this to the z-axis. Okay. Now there are a few different ways to set up motion. The simplest is just to actually click on this plus sign here and define a rotational speed for the shaft. You can also write a script for your own mathematical equations. But for the sake of this purpose, I'm just going to keep it simple and define an RPM right here. Okay. Now what I like to do is just make sure that this thing is working properly. You can come down here and there's a play button and we can actually see a little bit of motion. Looks like it's rotating in the right way, so it's good. Also, if you don't want to use the play button, you can grab this red bar in this cursor and you can manually play this motion. It's a nice little feature. Okay. Now I want to set this rotation about its geometric center. So now I should be rotating about the center of this shaft. And now I'm going to go ahead and do the same thing for our other gears and shaft. I'll go ahead and make them a different color. Okay. I'm going to make this a blue one. There we go. Nice little color. Kind of show something a little bit different. That way you can differentiate. And let's go ahead and do the same thing here. We'll find our center. And let's set a rotation speed on this one. Oh, can't forget to change this to RPM. I've fallen into that trap a couple times. Let's make this a different speed. And let's test it, make sure it's working. All right, perfect. Now we've got some motion going on here. Just like that, it's really easy to set this stuff up. Again, no mesh is required up until this point, and that can save a good amount of time. You don't have to fool around with any mesh, and we can keep plugging forward and start moving towards the simulation. Okay. So now I'm going to go back to our wizard, which can be accessed either here, or I'm just going to go ahead and plug this out right here. So now I'm also going to define a fill, and I'm also going to give this some direction. Click on this. We'll go to our objects, and let's go in the Y lower direction. One thing to note is in this fill, it's always important to make sure that we're not interfering with any solids, any place where the fluids cannot be filled. I've run this mistake a couple times, and it's an easy fix, but to save a little headache, just make sure we're not interfering with any gears or any shafts. Let's see. All right, perfect. And so now I'm going to go ahead and set up some physical properties for this. Uh, um, this can be access to the physical property manager. I'm going to set up a fluid, some oil. This is just kind of some examples that I'm using right here. I'm not going to go into too much detail about these. Okay, I'm going to go ahead and add a polygon. This is just for our wall geometries. I'm not going to change anything here. I'm just going to keep it as a standard default here.
Chris, while you're setting those physical properties, we did have a question from Bill on overlapping boundaries. So he asked, because in this simulation we haven't set the motion on all of the gears, are we going to get errors when he runs finite volume CFD? Overlapping meshes can be a huge pain. The answer to that is no. So with the way walls are defined in the MPS method, there's no real penalty to having overlapping boundaries. So they basically just cancel out each other, or not cancel out, but they don't interact with each other. They only interact with the fluid. So if they're overlapping, there's really no difference to having one wall there or two. And this can make your life a lot easier. One, for iterating geometry when your CAD files are, something's defined twice, or if you don't want to spend, half an hour trying to get the exact right rotation on a gear or something like that. But back to you, Chris.
Okay, perfect. Thanks for that brief explanation. So what I've gone ahead and assigned all the polygons to our walls, our gears, and I've also assigned this oil to our fill, our particle fill. And I'm going to keep continuing on in the wizard. I'm going to go ahead and change our length to millimeter. And for this case, I'm going to do 5 millimeter particle size. And decreasing the particle size will increase the computational time to run the simulation. I did this model yesterday afternoon, and again yesterday evening. It took me about a couple of hours to do it, so that's some significant time, as opposed to conventional CFD methods that could take up to weeks to run a simulation. So I'm going to go ahead and continue. I'm going to go ahead and change our gravity direction. I'm going to go ahead and change some properties here. Again, this wizard is very easy to use. It helps in guiding your simulation and pre-process. So I'm going to change this to 5 seconds. That way we can increase the time it takes to actually solve this thing. And go ahead and change this up a little bit. Perfect. I'm going to make one quick change. This is kind of an advanced setting that I'm going to do. I'm not going to go into heavy details. This will actually help increase the time it takes, or excuse me, decrease the time it takes to solve this in the simulation. That way we're not spending too much time or running to too many errors. And this is just kind of a best practice for gears. Again, it's a little bit more advanced, and I won't get too heavy into details. So I'm just going to go back. Oops, sorry about that. I'm going to go back to the wizard just to keep sake with this, and I'm going to go all the way to the end of our wizard. Now I'm going to go ahead and click execute, and I'm going to go ahead and pre-process just to make sure that everything is filled properly and the particles are there. shouldn't take too much long. While we wait, I guess, is there any questions up to this point?
So we do have a question from Mike, and he asked, you've used a fill in this problem. Do you also support inflows and outflows?
Yes, it can be done. The very beginning, you can define your inflow, and you can also define an outflow. In this case, all the fluid is actually encased within this this enclosure, and so there's no need in this example to define either an inflow or an outflow. We just simply just select a fill, and we'll simulate from there.
Okay, thanks, Chris. And we've also got David from New York. He asked, it sounds like you can do small problems on a workstation or laptop. What's the workflow like for much larger problems where that's not feasible? So the short answer is yes, you can run, most of our customers run the vast majority of their simulations on either their own work laptops or on company workstations. For people that are doing much larger simulations, or they just they have all of their big resources on a cluster, we do support cluster computing, and I actually use that internally for larger simulations. So you can basically package up all of the settings that you assign locally on your computer, so you can set the whole thing up and then basically ship it to the cloud, run it there, and then pull the results down and do post-processing again on your local machine.
All right, thank you, James. Now that we've got all the particles in there, this is a good sign. Looks like everything is filled properly. If there is an error with your fill, this typically won't show. But let's go ahead and preview it and make sure everything is working properly. Okay, so we haven't nothing's actually happened. We haven't actually solved the system or the simulation yet. So just want to make sure that everything is running smoothly before we do that. And I'm going to go ahead and, instead of going to the wizard, I'm going to use a little shortcut. You can use this little play button. Since we've already run the pre-process, I'm going to use the simulation. Now I'm just going to go ahead and execute this. Now this may take a little bit of time. I'm not going to let this whole thing run. I've got a separate model that I've already solved. Just want to get this going a little bit. And if you notice, you go back down here, you'll see a blue bar. This will tell you that up to this point we have results thus far in this simulation. So I'll let it run for a couple more seconds, and then we can press play and kind of see what's happening.
While that's running, we also had another question from Andy, another Texan. So he asked about complex motion. So in this problem, we've done simple RPM, which you can just define as a number. So to answer your question, you don't need to use the multi-body coupling. That was record time that I had mentioned earlier. You don't need that to define somewhat complex motion like a piston moving. What you can do is use the script that Chris had mentioned earlier. So you can define multiple reference frames and somewhat complex motion. It can be a little bit easier if it's already defined in a multi-body tool, or if you want that two-way coupling, like in the chain example that I showed. So I guess the short answer is not always.
Okay, let's see how much we've got right here. And I'm going to slow this down just a little bit. We can see what's actually happening. And we can see so far that our simulation is running smoothly. The fluid is acting in a similar manner that we would actually see in a real-life application. And that's good. That's perfect. That's what we're looking for. So I'm going to go ahead and stop this just so I can not take up too much time. And what I can show you is I can show you a model that's already been complete, solved, and that way we can all see what these results can actually look like once a full simulation is complete. And this is a full model here. Let me make sure there's nothing going on with my camera. And this is going to be a completed model right here. Again, this model I ran last evening, I actually changed the particle size to 4 instead of 5. And this one took me roughly about an hour and a half to set up, or the model took a couple of minutes, probably 15, 20 minutes to set up, about an hour and a half to run the simulation and get the full results. So far, even in this application, it's a significant time reduction as opposed to the conventional CFD methods. And again, I'd like to point out that no creation or resizing of meshes, excuse me, was needed for this application or in the software. I guess we can open it up if there's any other questions at this point. Just let us know and we can answer them.
Yeah, it looks like we have another Chris. So there's a lot of Chris's in this call. So Chris from Georgia is asking, what about post-processing? Does that have to be done in another software tool? So no, we have a huge array of post-processing tools built into Particleworks. So you can map values onto the actual particles using the color map. You can generate surfaces if you're trying to look qualitatively at what's happening. You can do cut sections. You can also get CSV files with a lot of output parameters, and then you can do graphs in Excel, things like that. Okay, so so here's Chris.
So thank you, everybody, for taking the time to join the call. We have put information on the screen now. For more information, you can contact us directly on email. James and Chris Garcia were the engineers that were showing the actual case studies and the demonstration. The website has additional information, including probably about 10 or 12 different case studies on gearing with the meshless methods. We have some papers that have been presented at different conferences that we can share if you need to get information shared internally. And finally, if you'd like for us to set up a demonstration for you at your particular company, please let us know, and we'll be happy to set that up. We'll be following up with everybody on email, and we thank you for your time today.